Alrighty, let's take a look at trig equations. Now to do trig equations, I'm going to go back to one of our earlier lectures we had. This is a while back. And this is when we first defined trig functions and the properties of trig functions. Now, we introduced some fundamental identities earlier. I just want to review these before we actually do some trig equations, because sometimes, not always, but sometimes these identities come in handy in our work. So then it's always good to review them together, right? Thus, here are a few set of identities for us. We have the reciprocal identities here, correct? Cosecant, 1 over sine, secant, 1 over cosine, cotan, 1 over tan. And then we have our ratio identities, tan and cotangent. We have the Pythagorean, famous Pythagorean identity is here. And we also have the byproduct of Pythagorean identities. If you want identities involving secant and cosecant, we pretty much create them on demand. We don't, if you can memorize them, it's your choice, but I like to create them as I go. And then we also talked about even odd properties, which gave us the negative angle identities, right? All these trig functions except cosine are odd. It means the sine or the trig function of a negative angle will be negative of trig measures of a positive angle, with the exception of cosine and secant. Doesn't matter whether you do theta or negative theta. Those values will evaluate to the same outcome. Okay, so again, this you've seen before, and let's see how things are gonna turn out. Now, when it comes to trig equations in this section, we're gonna have at least 3 different kinds of trig equation. The first kind we have is where we have a single trig function. A single trig function. So you have just a sine, a tangent, secant, whatever. And then another one, your trig equations involve quadratic expressions. So these could be quadratic in form. So for example, I may have sine squared, cosine squared. And you have those where you have to use other identities, using other identities, such as Pythagorean identity. So let's take a look at these. These aren't actually too difficult. They're pretty basic. So let's say I want to start with this one. I want 2 sine squared theta minus 1 equals 0, and I want to solve this one. Okay, and I want all solutions, all infinite number of solutions. So how are we going to do this? Well, let's isolate this sine squared, add 1 to both sides, divide by 2. And then the next step, we're going to take the square root, right? When we take the square root, don't forget we have plus or minus, correct? 1 over root 2. And at this point, again, most of the exercises that I do anyway, and they're in the books, math books, they have them to where we want exact values. Again, we don't want calculated values that are rounded. Okay. And a lot of these work with the special angles. Those are 30, 45, 60, and then remember the quadrantal angles. 0, 90, 180, 270, and 360. So this one, sine theta, is 1 over root 2. And at this point, we say, okay, well, 1 over root 2, that's going to be 45 degree. Correct? 1. This is root 2, and this is 45 degrees. Now, plus, well, sine could be positive here, or sine is positive in the second quadrant, right? It's also going to be 1 over root 2, therefore, this is pi over 4. This would be 3 pi over 4. Now, the negative values kind of work the same way, right? If you extend these lines, so this would be, for example, that's a negative angle. and this is a negative angle. This one would be 5 pi over 4, and this is 7 pi over 4. Okay, so how are we gonna write the solution for this one? If I wanted 0 to 2 pi, it's gonna be easy, right? If theta is in 0 to 2 pi, then you're looking at the answer. Then the solution is going to be what? It's going to be pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Correct? If I want all solutions, that was my initial intent, all solutions, then I can think as such. I'm going to say, well, pi over 4, and then 180 degrees later, I'll pick up this one. And then the subsequent, if I think about a circle, each time I rotate around the circle, I can pick up more solutions, right? So there you go. Let's say I start here. I can go 180 degrees later and pick up this one, go back 180, not back, but go forward. Continue forward. Each time I move forward, I'll pick up another one. And then in the opposite direction, it works the same way, right? Okay, well, we can put all this together in terms of multiple rotations around the circle. Therefore, the solution to theta is, we start at pi over 4 plus k pi. That picks up everything and all the subsequent rotations around the circle at pi over 4 and 5 pi over 4. Okay, and then same idea with 3 pi over 4 and 7 pi over 4. Notice from pi over 4 to 3 pi over 4, that distance is 90 degrees, right? So I couldn't do this unless I kind of start at pi over 4, right? And then add a multiple of 90 degrees to it. That would work, right? K pi over 2. Yeah, maybe that would be a better option. Sure, let's do that. Now that I thought about it. So I go 90, 90. Yeah, that works out perfectly. 90, 90, 90, 90, 90. Like, okay, let's do that. So it's going to be pi over 4 plus k pi over 2. All multiples, 90 degree multiples will do. So I don't have to do two separate expressions for those. Perfect. Glad I looked at it. And there we have. This one is solved. Now for the next one, for the feature ones, we just want to go 0 to 2 pi. Okay. Now this time, let's say I have cosine of multiple angle 2 theta equal -1/2. What's important is that I have a single trig function, cosine. So it doesn't matter if it's 2 theta or 20 theta. That's like cosine alpha equal -1/2. Cosine of some angle is -1/2. Let's see, cosine of what angle is -1/2? Well, cosine could be negative in the second, right, or third quadrant. In the second quadrant, cosine of 60. I know cosine 60 is 1/2. So there you go. Therefore, this is going to be -1, 2. And continue on. This will be 2. Remember, the hypotenuse is always positive regardless of the quadrant we are in. We allow for the sides to be positive or negative. And here's the other one. So 2 pi over 3 or 4 pi over 3. Both of those are solutions, right? And therefore, now I want the solution in 0 to 2 pi. So here's how we do now. Because this is the measure of angle 2 theta. So I'm going to say 2 theta, the measure of the angle, is going to be 2 pi over 3. And then every 2k pi for all the subsequent, again, rotations around the circle. And then at 4 pi over 3, and then all subsequent rotations around the circle. Okay. Therefore, divide everything by 2. I get pi over 3 plus k pi. That will pick up a bunch of solutions. And then let's do 2 theta equal to 4 pi over 3 plus 2k pi. Divide by 2, I get 2 pi over 3 plus k pi. We get this one. All right. Now, let's actually plug in values for k and pick up all the solutions from 0 to 2 pi. So remember, k is integer. In all of this work that we do, anytime you see k anywhere in my notes, k is an integer. Okay? The integers are like all the whole numbers and their opposites, except 0 is 0. Opposite of 0 is 0. All right. So let k be 0, then the solution is pi over 3. When k is 1, I'm going to do my scratch work here. So that's pi over 3 plus 3 pi over 3, or 4 pi over 3. So I'll pick up another, there we go, 4 pi over 3. So the next one would be another 3 pi over 3. That's going to be 7 pi over 3. Okay, now let's see, 7 pi over 3, well, 6 pi over 3 is 2 pi. So that actually, 7 pi over 3 exceeds 2 pi, doesn't it? We just want 0 to 2 pi. So there's nothing wrong with 7 pi over 3. It's just not what we want in that domain, 0 to 2 pi. So I'll pick up a couple of solutions there, and I'm going to pick up a couple of solutions here, I'm sure. When k is 0, we get 2 pi over 3. Let's bring this to the mix. When k is 1, we get 2 pi over 3 plus pi, and that's 5 pi over 3, just shy of 2 pi. 5 pi over 3, and we stop. There you go. So that'll be the solution to this trig equation. All right, we picked up 4 distinct solutions in 0 to 2 pi. Now let's take a look at another one. This one, suppose I have sine of the half angle equal negative root 3 over 2. So this time sine is negative. Well, sine can be negative in 2 quadrants, correct? Could be here, negative root 3 over 2. That's one. Or it could be negative here. That's negative root 3 over 2. Correct? That's one. And here's the other angle. Sine is negative in the 3rd and the 4th quadrant. Therefore, the measure of the angle here is, for the triangle, is 60 degrees. All right. Let's do this. Now 60 degrees, the measure of angle is going to be, that's 180 plus 60. This is going to be 240. 240 in terms of multiples of 60, that's 60 times 4. Correct? So that's going to be 4 times 60, and 60 in radian is pi over 3. Okay, 4 pi over 3. I'm going to set the argument of the sine, theta over 2 equal 4 pi over 3 plus 2k pi, which allows for multiple rotations around the circle. Multiply everything on both sides by 2. This will give me 8 pi over 3 plus 4k pi. That will pick up all infinite number of solutions. Okay. And that takes care of this angle, the one I just did, the 4 pi over 3. The other measure of angle is going to be this one. Now here, this angle is 60, therefore the measure of the angle here is going to be 300 degrees. Again, that's 5 times 60, or 5 pi over 3. Cool. Now I can generate a few solutions for that. Theta over 2 is going to be 5 pi over 3 plus 2k pi. Multiply everything by 2. Theta is going to be 10 pi over 3 plus 4k pi. Good. Now we can generate the solutions, starting with this one. When k is 0, we get 8 pi over 3. And then we add 4, k is 1, we add 4 pi to that. Now 4 pi in multiples of, let's say, 1/3, that would be 12 pi over 3, right? 12 and 8 makes 20, so that's 20 pi over 3. Okay, and then the next one, you add another 12 pi over 3, you get 32 pi over 3. When do I reach 2 pi so I can stop? Well, 30, yeah, if I go one more, 32, yeah, because I'm thinking 2 pi, right? 8 pi over 3. Let me think. Okay, I see what's going on. All of these solutions are actually greater than 2 pi, aren't they? Like 8 pi over 3, because 6 pi over 3 is 2 pi. But that's okay, because we want some solutions out of this. Otherwise, there will be no solution, and we do want this to have a solution. So forget the 0 to 2 pi for this exercise, or this example. Let's just generate 3 from each of those. So let's pick up 3 solutions out of that one. When k is 0, we get 10 pi over 3. Again, if you go 6 pi over 3, that's 2 pi. So with 10 pi over 3, we are already exceeding that, but that's okay. Because when you go in here, remember, you divide the angle by 2. So that will change it anyways. All right, and then let k be 1. And when k is 1, 4 pi, that's 12 pi over 3. 12 and 10 makes 22 pi over 3. And another one, 12 added to that. 12 and 22 makes 34 pi over 3. And there you have it. So we have 6 solutions. None of these are 0 to 2 pi. Every one of them exceeds it. But that's okay. These are the solutions. And there's countless others. Let's take a look at another example. So for this one, this is the one where we have like quadratic in form, right? This is a quadratic equation in sine theta. So how are we going to work this? Well, we're going to do this as if I'm doing a quadratic equation. For example, 2m squared negative m minus 1 equals 0. So think about how you would factor this. Let's say you go 2m and m, and then let's go plus 1 minus 1 equals 0. That should work. Yep, that'll do. I'm thinking the OI, negative 2 and 1 is negative 1m. Yep, that would work. So from this we get 2m plus 1 is 0, or m minus 1 is 0, so m is 1. M is negative 1/2. Okay, so this one works the same way. I'm going to factor this as 2 sine theta plus 1 times sine theta minus 1 equals 0. And then we can solve this by 0 factor property. Therefore, sine theta equals negative 1/2, or sine theta equals 1, just like the m version of it. Cool. Now at this point we say, okay, well, sine of what angle is negative 1/2? And let's see, sine of 30 degrees is 1/2, right? Now negative, so the angle must be in the 3rd or 5th quadrant. This is 180. That should be 210 degrees. Okay, so that's going to be 7 pi over 6. Correct? That's 7 pi over 6. And let's see. Let's find another one. The other one, this would be 30. That's 330 degrees, right? Which is 11 times 30. That's 11 pi over 6. All right. So I can write this as 7 pi over 6 and 11 pi over 6. That will give me two solutions there in 0 to 2 pi. Now sine theta equal 1, well, that should be a quadrantal angle of pi over 2. Sine of 90 degrees is 1. So all in all, there are 3 solutions, and we're going to keep this one in 0 to 2 pi. Okay, the key here is your factoring skill. Remember, those skills never go away. All right, let's take a look at another example here. This time I'm going to have 2 different trig functions. Let's say I have tan theta equal to sine theta. Okay, now I'm gonna solve this 2 different ways, and let's see where this is gonna go. Now one way people do it is this way. Tan theta, or I should say can be done is this way. However, there is a caveat. Sine theta over cosine theta equal to sine theta. Okay, and then we can divide both sides by sine, so we get 1 over cosine theta equals 2, right? And swap out the 2 and cosine, so from this we get cosine theta is a half, and then we can say, well, cosine of 60 degrees is 1/2, and cosine of 5 pi over 3, 300 degrees, right? I'm thinking cosine here. This is 60 degrees. Cosine of that is a half, and so is 300 degrees. So we picked up 2 solutions. Now, is there anything wrong with that? Let's keep that one for now. Let's do this a different way, and see if there was anything wrong with what I just did, the way I solved this. And by the way, a lot of people do it this way. However, let's see what happens here. An alternate method is doing this. I'm going to write tangent, just like before, as sine theta over cosine theta equal to sine theta. And because cosine theta cannot be 0 here, right? We know that. It can't be 0. Because if that's 0, then tangent is undefined. So we assume all these equations are legit within the domain in which they are defined in. So I know cosine theta cannot be 0. So writing as sine over cosine, I'm not dividing by 0. I'm okay. Now let's cross multiply this one. So I'm going to get sine theta is equal to 2 sine theta cosine theta, which I know some of you recognize this as an identity, the right side, but we'll get to those later on, about 3 lectures from now. But let's continue on. What I want to do next is I'm going to move sine theta to the other side. So at this point I have 2 sine theta cosine theta on that side, negative sine theta equals 0. Okay, and we'll subtract sine theta from both sides. Next I'm going to factor. I'm going to factor sine theta, and I get 2 cosine theta minus 1 equals 0. And by 0 factored property, each factor may be 0. And of course I get the familiar cosine theta equals a half, which is exactly what we found here, right? So the solution to this portion is just as before. So I'm going to pick up pi over 3 and 5 pi over 3. Now, what about this part? Sine theta equals 0. Well, I can get a 0 out of that, couldn't I? When is sine theta 0? Well, theta is 0 or pi, isn't it? So notice I pick up 2 more solutions that I did not pick up here. Then what's the culprit here? What's the caveat? Well, it has to do with our very first step. Notice when I divide both sides by sine, I'm actually removing solutions. And the other thing is that I don't know what I'm dividing by when I divide by sine. Notice sine theta is 0. So when I cancel this, in effect, this is how they think of it, as canceling them as this way. What allows me to cancel them is the following. I can divide both sides by sine theta. That's what canceling does, and gives me 1 over cosine theta equals 2, doesn't it? Well, right in here is the trouble. We cannot cancel these, because to cancel is to divide by sine theta. And sine theta is 0, so you're dividing by 0. And guess what happens when we divide by 0? Division by 0 is undefined, isn't it? So it's for that reason that we cannot cancel these functions. In an equation in general, remember, do not divide by a variable. So if I have, for instance, I don't know, x squared equal x, something like that. Don't divide both sides by x and say that's 1, that's x, and I solved. You see that? Because you don't know what we're dividing by. Indeed, in here, again, my made up short example. We did divide by 0, didn't we? Look at it this way. X squared minus x is 0. Factor the x. And right in here, x is 0. So by dividing by x, I divided by a 0. A lesson to be learned. So please be aware of that. Do not divide by trig functions or variables unless we can defend it and say, well, I know sine theta is not 0 because, for example, I'm working with an angle that's in between 30 and 60 degrees. Then you're allowed to do it, but in general, you cannot. And we were not told that in this example. Okay, so let's take a look at another example. Okay, so here I just real quick wrote down an equation. So let's try to work this one. For this one now is one where we can actually use an identity. Notice, by the way, I have 2 different trig functions, right? Sine and cosine. One of them is in squared form, the other one is not. So I need to get either everything in terms of sine or everything in terms of cosine. Okay, now it's a lot easier to go from sine squared to cosine squared than it is to go from cosine to sine. How do I change from cosine to sine? Right? The squared form is easy because remember our Pythagorean identity? We said sine squared plus cosine squared is 1. Therefore, we can replace sine squared by 1 minus cosine squared. True? And that's indeed what I'm going to do. I'm just going to write this as 3 times 1 minus cosine theta. And I'm going to change my sine squared to 1 minus cosine squared theta. Now, a couple of ways we can do this one. Method number 1. Because I have cosine squared here, move cosine squared to the other side. So it's positive now. Distribute 3 to the binomial, so I get negative 3 cosine theta plus 3. Subtract 1 from both sides equals 0. So this will give me a quadratic equation, which is legit. This is fine. If you like it, do it this way. Good thing about math, it gives you options in doing things. You don't like one way, chances are there's a There's another way, perhaps a better way of doing it. And there you go. Now you can solve this. Okay. So if I solve this, I'm going to go, again, quadratic in cosine. So it's going to be cosine, cosine. Right? Now, two numbers multiply to 2. They add to -3. So I'm going to go -2, -1. And there you have it. Factored form. And then we can solve that. Let me put this on hold. Okay, let's come back here. Now, another way to do this is to, and I'm sure probably almost most of you like what I just did and I put it on hold. The other way is to actually use factoring to factor difference of two squares. So this is 1 minus cosine theta, 1 plus cosine theta, correct? Difference of two squares in factored form. This is what I did. A squared minus b squared is a minus b times a plus b. Right? That's what I did. Now, remember what I mentioned earlier? In here, something we cannot do. Divide by sine theta. That's exactly what it is here. I'm very tempted to do this, right? But we cannot do that, because if I do that, I'm eliminating solutions and I know I'm dividing by zeros. So how else can we do this? Well, let's bring this expression to the other side. So now my right side, I'm going to write it on the left side. 1 minus cosine theta, 1 plus cosine theta, and bring this to the other side. -3 times 1 minus cosine theta equals 0. Okay. And now the correct way is to factor the common binomial. So I'm going to factor 1 minus cosine theta from this expression, leaving me 1 plus cosine theta, that's this one, and -3, correct, equals 0. Here's my first binomial factor. The second one is cosine theta minus 2 equals 0. So, two ways of doing it, and I'm not saying this was a better way. I just want to show you two ways of doing it. Let me erase my hold. Look at this equation. Look at this one. They're identical. These are the same, aren't they? All right. Well, if they're the same, that means our next step is going to be the same as well. So however you do it. Now I'm going to proceed to solve it. By zero factor principle, each of those factors may be 0. So we said 1 minus cosine theta equals 0, or cosine theta minus 2 may be 0. Now with cosine theta minus 2, 0, add 2 to both sides. Now think about cosine of what angle is 2. Cosine angle is 2. Going back to the graph of cosine. Remember, this is one cycle of cosine, and it just repeats like that. Well, the maximum cosine can be is 1. The minimum is -1, correct? This is cos x. So, there is no way the output from cosine can be 2. So that one is ruled out. That's impossible. So the only possibility here is for this to have a 0 is for 1 equal cosine theta, or cosine theta must be 1. Well, cosine theta is 1 only when theta is 0. So there is our solution. Theta equals 0. Okay. And there you have it. Examples of trig equations to solve. And we did quite a few examples, not bad. And we kept it under 35 minutes. All right, so we are done with this section. Our next section, we're going to look at trig identities in the next lecture. So thank you for watching again, and hope to have you in another lecture, another video. Thank you and take care. Bye.